Morning, students. In the last lecture, you have learned how to write Bison grammar, and you added some actions. That actions is called write parse, which is the reverse direction of the rightmost derivation. So let me make it clear. Left parse is the sequence of production rules in your leftmost derivation. But right parse is a sequence of derivation rules in the rightmost derivation, but in reverse. So you know the meaning of why should be reversed, because it is a bottom-up parsing. I explained it in the shift-to-reduce parsing method. So you may take a look of the, imagine the conflicts, which is a kind of kind of the situation in dilemma, what to do. So one case is shift to reduce parsing. So it can shift the input portion to the stack, or it can reduce the stack top portion. So it is called a shift to reduce parsing, shift to reduce conflict. But in other case, it may be in conflict of reduce to reduce conflict. That means which part of the stack top should be reduced. It cannot be determined in that case. So you have two kinds of conflicts. But now, for now, you just think about it. If you got any conflicts, you have to rewrite your grammar in an unambiguous form. Okay. So in the last lecture, you have written ambiguous grammar, which was expression grammar, which will recall the conflicts. So let me just take an example, simple example. So in the compiler, sorry, comp 21, so you have made a simple.y in that case, which is unambiguous version of this one. So, but you may write this as ambiguous y. So in your ambiguous grammar, you may want to make it as exp. So that means you can make, this is ambiguous. If you have term plus term plus term, you cannot determine the plus is associated to the right or associated to the left. You cannot determine it. So this is inherently ambiguous. So even though you are changing this as a direction, so let me just take a look of this. Oh, sorry. It should be written as ambiguous. Sorry for that. Right. Edit ambiguous. So this is your ambiguous version. In your terminal, you may execute Bison EY ambiguous.y. So it complains one shift to reduce conflict. Okay, so let me just take a look of why it is in shift to reduce, why it occurs shift to reduce conflict. Just enlarge this a little bit. So if your input is num plus num plus num, your stack input, your input has num plus num plus num. This is the input end marker, and this is a stack bottom. So it starts a shift num plus n plus n. Okay, but it may perform the num is reduced to Tom. So t plus n here. But Tom may be reduced to exp, or it can shift n to here. So one option is, so let me just make it one option, option one, reduce it by e, leaving the input. So this is a reduce action. And second option, maybe, so in different, in different color. The second option is that you may leave t here, and you may go for the plus here, plus n here. Okay. So I think this is a shift. So it is in the conflict of shift to reduce conflict, but this is a very acceptable case because it can determine a certain action. So in this shift to reduce conflict, Bison prefers shift, prefers to shift, because shift action means you are consuming your input. So you are eventually get terminated. So that is the more plausible action for Bison. So Bison prefers shift. So you may neglect shift to reduce conflict if you know what is your situation. So the shift means preferring shift means it is rightmost and right associative. So your tree may be like this, right associative tree. So this is the result of shift. Okay, because you are shifting, eating up everything, and there's no option, then your tree is constructed. And in the last video lecture, you have learned, so let me just go back to the unambiguous version. This is the unambiguous version and simple divine. And you're just making a constant message for every action, okay? But you can make an attribute grammar. So the grammar rules, this may be considered as grammar rules. So your grammar rule, CFG, expression, arrow expression plus t, expression arrow t, and t arrow n num. This is your grammar rules, okay? But if you are interested in evaluating some attributes, you can think about the attribute evaluation rules. So the attribute, maybe you may consider the attribute V, which stands for value. So if you think about that, the attribute of T, so T dot attribute V, T dot V is determined by the number. So the numeric value numeric value of n. Since n is a token, so you can make a numeric value from the actually lexeme of the token. And so some guys maybe consider this and the lexval rather than this. You may think about that more exactly, more accurately, and the lexval. So the lexval means lexeme. So for this rule, the value of left-hand side is the value of the term. So value of the right-hand side. For this case, you have two e's, so you may need a subscript. For example, you may subscripting this as 1. So the value of e dot v is the value of e sub 1 dot v plus t dot v. So this is your simple attribute evaluation rule. Then you can make this action, you can substitute these actions by these attribute evaluation rules. So you make hand coding to make an evaluator, expression evaluator. So let's think about this today as using your Bison compiler. So let me just save this and switch to your handout. So in order to use attributes in Bison, you know that there was an option that you have to make a lexval, you have to make a value from your lexical value. So you remember that in your T rules here, your attribute evaluation rules is that T dot V equals numeric value of n dot lexval. Okay, sorry for the bad typing. So you know that n is token, and lexval is called a lexeme. So you know that in your lexical analyzer Flex, your lexeme is equals YY text. So you may safely replace this YY text. But currently, the default type of any attribute is an integer. Int is the default type. Of attributes. So it is safe to make an integer value. So how can you make, you know that YY text is a type of character pointer. So how can you make a numeric value from character pointer? Know that there's a to I here, a to I, so which was derived here. This means stands for ASCII to integer. So you may say, please make this as a to I. Okay, but this process should be processed in your lexical analyzer And there should be a method. How can I transfer to this value to Bison? You want to transfer the integer value of your lexeme to the Bison. And that is the global variable YYLVAL. YYLVAL means lexical value. So as you know, the YY is just a prefix for preventing name conflict. And LVAL is a lexical value. And I said that the default type of the attribute is integer. So it is declared as int YYLVAL. Okay. So your Bison, you're setting in your lexicon analyzer, you're setting this, and your Bison is reading from YYLVAL to their action. Okay. So you are setting YYLVAL here. This is a global variable, and which stands for the lexical value. So you can do the similar thing with our previous version. So let me just make it. So your mutable terminal, you want to copy all of them to, let's just, so you can make that 9 and copy simple L, simple.everything, and your maker file to lab 9. So in your lab 9, you want to edit simple.y. So this is the same version to your previous one. You can edit simple.l, which is a lexicon analyzer. And you know that in this case, you can may return it, but you may set YYLVAL as 0. Okay, 0 is too primitive. Let's make it 1. Okay, let's make it 1. Then in your Bison, you can use that value from dollar form. So you may print it, printf sending. Well, it is just the reverse direction, so you can make it as like this. Sending arrow sending new line. Okay, and the first value, so you may declare some variable of it. So the first value, how can I count the variables of Bison is that this one is in positioned by 1, 2, 3. And the value, you know, that value should be dollar. So you want to make a value of them. So what is the attribute value of 1? This one is called $1. This one is called $2, even though it is not setting. This one is called $3. So how about this case? $1. How about this case? $1. So everything in every values, every attributes in the right hand side is referred by $some number, positive number. And the value of the right hand side is called $. So this is also $. So you have to transfer T.3 is called N.3. If it is transferred correctly from your lexicon analyzer, so you have to set it. So let's make it from the bottom line. Okay, save this. I have to change this here. So how about to make this? Okay. So this case, T is $, T.V is $, and num.V is $1. So you are setting T.V as num.V. And you want to print an expression. Your numeric value is derived by T.V. Okay, with new line. So your numeric value, num, let's make it clear, num.value is derived T.V. So what is the value of num? $1. $. Okay. So let's do the similar thing to here. EXP is $, and term is $1. So even though it is similar to here, sorry, I have to change this as printf. Similar to the last one, is different. Different arithmetic values, T.%D, arrow. So it is the reduction. It is not what is good notion. So let's make another arrow. This one. So it is not derivation, but how about this is the reverse direction of derivation. Okay. Comes from okay. So this is good. Sorry. Comes from produced by EXP $%D, and you know that this is $1 and $1. Okay. How about the last case? $1 equals $1 plus $T, $3. Okay, so you want to make, so let's make it in, sorry, it is not good for the annotations. So E%D plus T%D is derived from E%D. And the first one is $1, $3, and this is $. So let's make it more short in here. So in this case, you can make, but beware that they are not evaluating it correctly because your YYL value is currently always 1. Okay, so it is just counting the number of operands. So so you can make it. Let me just to make it. And today's value is not OP, but OP, 1 plus 2 plus 3. Okay, so the value should be 6, but it is counted as 3. Okay, so to make it more good for evaluation result, you have to change the lexical value, simple.l. You want to make it, so to do that, you have to include stdlib.h. This is for h1. So for h1, make text, and then return num. Then it will correctly calculating the value of 6, 1 plus 2 plus 3. So saving this, make it only the flex file is changed, and your 1 plus 2 plus 3 make it 6. Can you find the 6 here? It is evaluated 6. Okay, so I intentionally write these forms in reverse direction because it should be in accordance with the, just executing it again, 1 plus 2 plus, in accordance of the derivation, you know, that the derivation sequence E double arrow E plus T, and this should be a rightmost derivation, rightmost derivations, and T should be none. Okay. And then E, what's wrong with this? T should be known, and E should be E plus T. E plus T, this is rightmost derivation, so it is none. And T should be none. It should be not a none plus none. And E double arrow should be Tom plus none plus none. Even though it has a single non-terminal, it is rightmost derivation, and none plus none is your final form. So you can think about this derivation is found here. Okay, so 1, 2, 3, 4, 5, 6. So 6 comes, 6th step here. And 5th derivation found here. Okay, and this derivation found here. So it is 5, so it is 4, and it is 3 here, and it is 2 here, and it is 1 here. So it seems like I, but it is not. So you know that this sequence is in reverse direction of your rightmost derivation. So this is called right parse. So no attributes is set for tokens for these things, operators, okay? Other tokens other than none. This is just a single note. And today's problem is expression evaluator. Write a program using Flex and Bison, reading an expression from standard input and printing the value of expression to standard output. You should start with the following grammar. So this grammar differs to the previous one because the operands are all added up more operators, you know, that times and modular operators are added. And another thing is that unary operators, these are the unary plus or minus, or parenthesized expression is added. So this is a typical expression grammar, unambiguous expression grammar. So note that usually minus and plus operator are included in the grammar verb. Based on the experiment, make a report with references. Assignment 6. You can write a report in Korean. Your report should contain the following materials: to propose your Flex and Bison input, and what you have learned in this laboratory. So your program should read from standard input. The input consists of a single line containing an arithmetic expression. Only 5 operators with parentheses with positive integers. So you don't want to handle signed numeral. Only the positive integers are allowed here. Also, spaces and tag characters may be included in the input. The program should print to standard output, just print the value of expression in a single output line. The following shows some sample input and output. So let's calculate the first one. The first one, plus 25 times minus 2 minus 3. So in the rightmost derivation, in reverse, you have to make this as a number. So plus num, okay. And then plus num is, so let's just take a pic of this one. Num should be vector, and plus vector is reduced. So this is the reduction step, not derivation. Sorry for this is reduction step. Plus vector should be vector, and vector should be term. And then you are considering this times, and you are doing similar thing here. So let's compute this. Let's compute this minus 1. It is not good. So you know that what is my intention. So in this reduction step, in these reduction steps, your Bison is doing actions corresponds to Bison actions. And Bison actions is just for calculating the value $, of this one, the star symbol. So once your star symbol $, is computed, you just print it. So your print should be performed as from the outside of YY parse. So in your main function, you are executing YY parse, and after that YY parse, you may want to printf %d with a new line, okay? And sorry for this. And the value you can make your own value. So just make it as binary value. You can declare global variable into binary value. Okay. Then you can print it here, binary value here. And your binary value is set in this, your action. You can make it binary value is set by $. Okay. So let's do another example for that. So rather than executing all of these, you just want to make it your final value is set as $. Okay. So rather than printing all of these things, sorry. So this is another EXP term. So your final value should be set as $. Final value. So rather than this is not final value because the term is not your star symbol. Okay. And where is your final value? You should declare here and final value as 0. And your final value may be printed after YY parse. Print that sending the final value. Okay. So doing that, make it. So let me change the make file because after this EXP R or EXP. Let me just take a look. EXP R. So you EXP R. So let's make it. And EXP on 1 plus 2 plus 3. Final value is 6. Okay. EXP on 10, 11, 12, 13, 15, 16. Okay. So you can do this by declaring your new variable here. New variable is declared here. And that variable is set as the value of your star symbol. Okay, even though it is set in duplication. So in order to prevent that duplication, you need augmented grammar that is not covered today. So you can up to that time you can do this trick. Any questions to here? Okay, so let's go back to your handout. So this is the value, you have to check it. This is 1, so 25 times 1, 25. So for the second case, you have to check it by yourself, okay? So it is important for you to understand that the Lex is processing your lexeme and returning an attribute, your Bison, and Bison maybe evaluate the value of them according to your attribute grammar. So the attribute evaluation rules can be encoded as Bison actions, and then you can make it to compute the final result, okay? And the final result may be reported or recorded to the global variable, just as the global variable which is named YYLVAL, which is between the Flex and Bison. So you can declare some other global variables, your Bison and your main file, okay? So any questions up to here? So do you have any questions up to now? No questions? Then let's call it a day. See you next time. Bye. 수고하셨습니다.